sounds you're hearing there were from objects called pulsars. Discovered, those of you who were at Orbital last night might have actually seen pulsars as they came on stage, used in that intro. They were discovered 50 years ago this year by Jocelyn Bell at Cambridge. So she was using a radio telescope to search for something else entirely. And what popped up in the signals from the telescope were those sort of sounds, flashes of radio waves, incredibly regular flashes of radio waves. They had no idea what these things were. In fact, they were so regular, so unusual, they thought they might be artificial. And so they called the first pulsar LGM-1, Little Green Man 1, because that's what they thought those things might be, messages from extraterrestrials. Pretty quickly, as they found LGM-1, LGM-2, LGM-3 and more scattered around the sky, they realized that actually they were not from extraterrestrials, they were from natural objects, but incredibly strange natural objects. They're neutron stars, the remnants of stars that explode at the end of their lives as supernovae, and the central part of the star collapses in on itself. And this little animation just shows you what these things are like. This is the size, this is the sun, and if we sort of zoom in on the sun, we see the size of the Earth relative to the sun. It's about 100th the diameter of the sun, so the Earth is 100 times smaller than the sun if you measure across it. If you zoom in on the Earth, then a neutron star is only about 20 kilometers across. So a neutron star is about the size of a city like Greater Manchester. But it weighs as much as the sun, 1.5 times as much as the sun. So it's like packing the whole sun into the size of Greater Manchester. Incredibly dense objects. A sugar cube's worth of a neutron star would weigh as much as all the people on the planet Earth all put together. Incredibly dense objects, really weird, very extreme physics. Why do they flash like that? Why do they make those sounds that you just heard at the beginning? It's because the neutron star is spinning, and it's got a very strong magnetic field. And these beams of radio waves shoot out from the magnetic north and south poles, and as the star spins, these beams sweep across the line of sight towards us. So we see an effect like a lighthouse. So you get that sort of flash, flash, flash as the thing spins around and the lighthouse beam sweeps past. 50 years ago, those pulsars were discovered, and we're celebrating that anniversary this year. And I've invited along 2 of our pulsar researchers to tell us about what happened over those 50 years. So we've got Professor Ben Stappers, who's the lead of our Pulsars and Time Domain Astrophysics group, and also Dr. Sally Cooper. And I'm going to leave them to talk about what's happened over the 50 years.
Okay, thanks very much, Tim. Yeah, so what we're going to do is walk your way through the last 5 decades of pulsar science and just try and hit some of the highlights. And the first highlight we're going to hit is in the 1970s, which is a so-called double neutron star. So Tim already told you about one of these amazing objects, these neutron stars that are spinning really very rapidly. It was in the 1974 that the first ever system was discovered. There were 2 of these objects going in orbit around each other. So you suddenly got 2 objects the size of cities weighing more than our sun orbiting each other once every 7.5 hours. So that's just every 7.5 hours these objects are going around each other. And it turns out that because of the precise nature of the ticks of the clock every time this pulsar rotates, they're incredibly useful for tests of things like general relativity. So we're able to use objects like this to test whether Einstein's theories are correct or not. And so in 1974, Hulse and Taylor made the discovery of this observation, and they also realized that the orbit, the 7.5-hour orbit, is shrinking by 1 centimeter every day. So the orbit is getting smaller by 1 centimeter every day, and that's because it's giving off something called gravitational waves. And these gravitational waves were predicted by Einstein, and this was the first ever time that they'd been seen indirectly. And so this led to Hulse and Taylor receiving the Nobel Prize in 1993 for this amazing groundbreaking work. I'm now going to hand over to Sally, who's going to tell you about what happened in the 80s.
Hello. Some of you might quite like the 80s, and it was also a good decade for pulsars too. So up to the 80s, we'd only found pulsars that span up to about 30 times a second. And I say only, that's still pretty fast. But in 1982, we found a pulsar that spins 640 times a second. So if you just take a minute and second to think about that, that's an object that, like Tim said, is about the size of Manchester, as much mass as the sun, spinning 645 times a second. If you were standing on the surface of the star, you'd be traveling at 100 million miles per hour. So why does the pulsar spin this fast? Why is this one different? So it was predicted that this star was actually formed in a binary so that it had a companion. And as you can see, as the first star evolves, it becomes a pulsar like normal. But as the companion also comes to the end of its life, it goes bigger, forms a red giant, and the pulsar actually starts stealing gas from that star. And as it does, conservation of angular momentum, a bit like an ice skater, means that the pulsar begins to spin faster and faster. So what's unique about this one as well is that when we found this star that spins 645 times a second, it was found on its own. So then we've got a dilemma. Why is it found on its own if we predict it to be found with a companion? And that's because we've also found these things in the late 80s called black widow systems. And that's when the pulsar, once it's stolen mass from its companion, it then goes on to destroy it.
So that was the sound of a pulsar spinning 645 times a second. Again, it's not possible. Your ears couldn't take it. So in the 90s, pulsars also achieved a first. So we all know about the planets in our own solar system. And more recently, you will have heard of the discovery of lots of different planets outside of our solar system going around other stars. But it was already in the 1990s that the first so-called extrasolar planets were discovered. So these planets actually were orbiting a pulsar. They weren't orbiting a normal star. They were orbiting this amazing spinning ball. And the idea here is that we see our own planets in the solar system for scale on the left-hand side. And on the right-hand side, you can see these 3 planets that were formed. And it's completely unknown at this stage how they got this way, because we now know more than 300 of these systems, and no other system has planets like it. In fact, the innermost planet, two of the planets are around about 4 times the mass of the Earth, and they spin around the pulsar between 60 and 90 days. And the other object is the size of a moon. So it's the size of our own moon approximately, and it orbits something like once every 20-odd days. So we're able to detect objects like the size of our moon many millions of kilometers away, spinning around these objects.
So then we come to the noughties, the 2000s, and this time we have the double pulsar. System. So you saw earlier these binary systems, but in this case, this is actually 2 pulsars orbiting around each other. And their orbital period is 2.5 hours. So now you have 2 of these objects, something the size of Manchester, both spinning fast around each other in only 2.5 hours. That's 10 times a day they are going around each other. But the double pulsar system is important because we can test Einstein's theory of general relativity and tests of gravity. And so Einstein predicted that as light travels through space, it's actually bent by massive objects. And we can use the double pulsar, the timing of those 2 pulsars that's really accurate, to actually test that. And in fact, Einstein's theory of gravity is the most complete theory to date. And the pulsars, we're working to confirm that theory. And the double pulsar system is actually so extreme that we are finding effects that weren't even predicted to begin with. And so the double pulsar system is essentially our laboratory in space. and we can make tests with those. Yeah.
Okay, so let's bring us right up to date. And in the 2010s, what we're trying to do is use these objects, these pulsars that we could sometimes call celestial clocks, to make the most precise measurements we possibly can to try and detect effects that have happened 10 billion years ago, when galaxies were merging together. And in the center of these galaxies, there are black holes. These black holes we call supermassive black holes because we like superlatives in astronomy. And you see here these two objects, these two black holes, they actually meet when these two galaxies merge, and they actually will orbit each other. And because of the extreme environment in which they're orbiting and their masses, and because they're so compact, they actually generate these things called gravitational waves. These gravitational waves actually distort space and time. They can actually, as they pass through the Earth, it distorts the space and time around us, and that causes the pulses from these pulsars to arrive at different times. And so we can use these pulsars like some sort of intergalactic type measurement apparatus to actually measure these effects that were predicted by Einstein. And this is one of the key programs for telescopes like the one behind us for the coming decades. Thank you.
Thanks very much. Bit of tag team astrophysics for you there. One thing just to remember, just before we go off, is just that these things are incredible objects. They've been brilliant laboratories for testing extreme physics, and they were discovered completely accidentally. So we weren't looking for these things when they were discovered. A complete unknown, something about the universe we had no idea was there. We looked at it in a different way, and we discovered something new. And that's something that will always happen. So as we build new instruments, things like the square kilometre array we're building now, undoubtedly we will discover completely new exotic phenomena that will prove to be, we hope, as interesting as pulsars have been over the past 50 years. Thank you very much.